I would just quickly say a few words just to kick off, as I've been asked to. So I would just like to first thank the organizers of the seminar. It's really great to have our own online seminar series. So I'm quite excited to see what is going to happen. To have so many of you guys connected, like I can see many names of people that I could have only dreamed to get to meet. So this is really nice. And I would like to start by thanking Yasmin, Nagisa, and Kuan for helping set this up. And also thank members of the management board of the Bilevel Optimization Society, in particular Johannes and Victor, who helped to support Yasmin, Nagisa, and Kern to set this up. So really, thank you so much to get this off the ground. So yeah, we look forward to what's going to happen with this in the next few years. So, and also I have one announcement. As you all here probably are aware, we have our first international conference within the context of the Bilevel Optimization Society, which will take place from the 2nd to the 5th of August in Pittsburgh. I guess you've all probably seen emails on the conference. So the final deadline to submit your abstracts is tomorrow. So I don't know whether I've seen Johannes here. Please, maybe one of you add the link, put the link in the chat, please. So if anyone is considering attending and you've not yet submitted your abstract, so you have till tomorrow. If you don't know where to find the link, I think I could actually do it after this. So that's the announcement I had. Then finally, coming to the talk. So it's really a great honor for me to have Stephan again here. So for those of you who were here in Southampton 2.5 years ago when we had the Bilevel conference here, that's actually the last time I saw Stephan in person. So great to see him here again. As you know, Stephan was my PhD advisor. So he was my inspiration to do Bilevel optimization. And so I started my journey on Bilevel optimization with Stephan. So it's great to have this opportunity to meet him again after he officially retired a few years ago. So as you know, Stephan was a professor of mathematical optimization at the Technical University of Freiberg for many years. During that time, he took a lot of leadership role, which helped to push our field forward, supervised about 20 PhD students, wrote a lot of seminal papers, which many of us, if not all of us, draw inspiration from for our research. So Stephan, really a great pleasure to have you here again, and look forward to your talk, which I think the title is on reformulations of Bilevel optimization. So if there's no other interventions, Stephan, you can start when you're ready.
Okay, I'm ready. I saw many people attending already here, and yeah, it's a large, very large list, and I will thank the organizers for organizing that and make this webinar open for so many people from all over the world, and that is very interesting. Okay, now I will start and hope that you can see my slides soon. So can you see my slides?
Yes, it's all good. Thank you.
Okay. Yeah, then I will speak a bit about transformation of bilevel optimization problems to one-level problems, because if you want to solve them and to investigate them, then we can only do this for single-level problems. So we have to translate it, transform it, and here is my bilevel optimization problems. You see the lower-level problems. That's equation number 1 with a feasible set mapping. an optimal value function phi of x, solution set mapping. Okay, we know that the number of optimal solutions of an optimization problems is not in every case a singleton. And so this is a point to set mapping here, and we have the graph of this point to set mapping, and then we have here our bilevel optimization problem of minimizing with respect to x only, and not with respect to x and y, only with respect to x. An objective function f of x and y is subject to inequality constraints, and the constraints that y is a global optimal solution of this lower level problem. And so the question is why we have these quotation marks at the beginning. And the point is, if the set of optimal solutions psi of x does not reduce to singleton, then the function f of x and y is not clearly defined. And one way out of this situation is the optimistic bilevel optimization problem, and I will only speak about the optimal one, about the optimistic bilevel optimization problem. And this means that in the lower level problem, the follower will select one best optimal solution of his solutions with respect to the upper level objective function. And this means we have here in the inner this minimum with respect to the lower level solution. And this problem is almost equivalent to that problem in the equation 6. There are some exceptions of this equivalence, but in general it's equivalent. And so we speak about this problem 6. The problem is not convex, the feasible set is only implicitly given, and that is the difficulty. Here, that's not a convex optimization problem. It has been intensively investigated over about the approximately last 50 years in optimization theory, and this we can see in a bibliography from this joint editorial work with Alain from 2022 or 2020 about that. When did we do it? Okay. We have one example here, which I will use at several places. The lower level problem, linear optimization problem with right-hand side perturbations, and in the upper level we have only to minimize a quadratic objective function. It has a unique optimal solution, and this is seen here in this picture. The green lines here are the feasible set of my bilevel optimization problem with respect to x and y. And we minimize the distance to this point here, and this means 0, 0, 5 and 0, 5 here is the only, what's that? No, I'm here. Yeah, 0, 5, 0, 5 is the only global optimal solution, and there are no local optimal solutions. We will see this example later on again. Then I come to the first transformation. The first transformation is this optimal value transformation, where I replace the lower level problem by demanding that the objective function in the lower level problem is not larger than the optimal value function, and we have the feasibility assumptions also. The original formulation is from Utrata, and this problem is fully equivalent to the bilevel optimization problem. This means the global optimal solution of the bilevel problem is also related to global solution of this problem, and that's the same is also correct with respect to local optimal solutions. There's one difficulty, this inequality here. This inequality is an equation at every feasible point. That is clear, and this means that the non-smooth Mangasam-Fromowitz constraint qualification is violated at every feasible point. And this makes one more difficulty. Okay, this difficulty can be solved by using some perturbation, we're using this partial calmness assumption. This means that violation of this constraint here in this optimization problem is penalized by this penalization factor here. And then we get, in our case, if the function phi is a Lipschitz continuous optimization problem, we get here Lipschitz optimization problem. This function phi is Lipschitz continuous. We get a Lipschitz optimization problem. We can solve it as a Lipschitz optimization problem. The first point is that we get necessary optimality conditions as given here. This means that if you have a regularity condition satisfied at a local optimum, then there exists U and Z such that these necessary optimality conditions here are satisfied. And I know that these necessary optimality conditions have been solved by Alain and colleagues. And this can be seen then in the next. Okay, in the next slide. Alain used this Fischer-Burmeister function some time ago. And this Fischer-Burmeister function is given here. And this means that these complementarity conditions here are satisfied if and only we have here this equation. The difficulty in this equation is that the left-hand side here is not differentiable at the origin. And this means that Alain used then here in a smoothed function for approximating this, and solves then computed then optimal solutions of this problem here by using this Levenberg-Marquardt method for fixed penalization parameter. Yeah, for fixed penalization parameter V. And that they did, and it has been shown that this method can be used for quadratic convergence to a solution of our problem. And the last point is then to use some update of the penalization parameter. And and I think that this can also be done then if we use a penalty function method, for updating this penalization parameter in combination with say bundle algorithm to solve this Lipschitz optimization problem. Maybe this can be done. I have not seen. I didn't do that. It's only a suggestion which possibly can be done. Another idea to solve our optimal value transformed problem is by approximation of the function phi. If this function phi is convex, then we can do this. We can approximate it by using some piecewise affine function. And this piecewise affine function is given if we take some test points, say test points, or some selection of points xj. We need some condition here that the feasible set, is contained in the interior of the convex hull of these points that we need then for convergence proof. And then can we replace our function phi of x by this piecewise affine function here. That's a linear combination. We use a linear combination of our x, and we use then here also a linear combination of the function values, or convex combination, better as a convex combination of the function values, and minimize this function in place of the function phi, and replace the function phi by this function here, and then we get some approximate problems here, and we solve these problems. The next, what we have to do after solving these problems, we have to check if the solution of this problem here is feasible. This means that we have to check if yt is an element of x, psi of x of t is an optimal solution of the lower level problem. If yes, then it's okay. Then we have found a solution. And if not, then we have to add the point x to the set of all points xt, which we used at the beginning, and then we come to a new problem, and we have then to solve this problem 13 again. And the result is, if you do this by global optimal, by solving the problem, what was it, 13 globally, then we come to a global optimal solution as an accumulation point of the sequence of points we have computed. Okay, that is one idea which we did with another PhD student of mine, Susanne Franke, in 2016. And yeah, it is the first idea. We can also do this if the function psi is concave, then it's not so difficult. And yeah, that's my first transformation, of bilevel optimization problem to a problem which we can investigate. Okay, then I come to next. I found that we can use some dual problems to the problem 1. The first one is a dual problem by Wolfe, the other by Lagrange duality we can use, and Monveilleux duality we can use. I will only speak about Wolfe duality here. Wolfe duality, that's my dual problem to my problem 1. Problem 1 was minimization of x of f with respect to g of x and y not larger than 0, and that was it. And here we have to maximize the Lagrangian with respect to y and u. X is fixed, subject to the constraints that the gradient of the Lagrangian with respect to y is equal to 0 and u is not larger than 0 and not smaller than 0. Okay, and that is a dual problem by Wolfe from 1961. And we need convexity for this, or some type of convexity for this, to get weak duality. This is the idea to get weak duality. Here the first is convexity. Here the next one is then to use that the y gradient of the Lagrangian is equal to 0. So we come to this equation here. Then we use again convexity, and then here this is equal to 0, and so we come to a weak duality. Without convexity, that is not correct. We can weaken convexity a bit, but we cannot use it for general nonlinear problems. That's not correct. Okay, then we come to our result for weak and strong duality. The first is weak duality. Okay, the next is also again weak duality. And here, so we start with a feasible point for our lower level problem. Then we come to our dual problem. And the same is then here. And we can come also back if we have an optimal solution of the dual problem and need some assumption here, some regularity, for instance, then we can, when we have also an optimal solution of the original problem. And this is, of course, this regularity here can be replaced by strong convexity of the objective function in our convex lower level problem. That can be done. And so we have now more or less is this one relation between global optimal solutions of the problem, of the lower level problem and of the dual problem. Yeah, we can weaken this convexity by pseudo-convexity, and that is given here, and we can use this pseudo-convexity also for weak duality. Okay, and we can also come back. Strong duality is also possible. So here we use here Mangasyan-Fromowitz constraint qualification. It's a lower level problem, pseudo-convexity, and can get strong convexity. And a strong duality, sorry. And if you know that, then we can replace our bilevel optimization problem by this problem here. And that is a single level optimization problem, and this single level optimization problem can now be investigated. For finding relations between the bilevel optimization problem and problem 15, we use an abbreviation by the set KW here and come then here to this. We have a global minimizer of this this problem 6. That was, there's my 6, our bilevel optimization problem. Here, this is a problem 6. Okay, that's not. That's it. Here. Yeah, it's a global optimized solution of the bilevel for the bilevel optimization problem. Then for each pair of ZU and Z0 and U0 in the set here, we have a global minimizer in the replaced problem, and for a replaced problem, if we have a Mangasyan-Fromowitz constraint qualification, then we can also back. Okay, and that can also be done then under Mangasyan-Fromowitz constraint qualification. Okay, I come back to my example. Yes, that's the example we have seen. For this example, this dual problem or this transformed problem is given here. And if we investigate this, then we see that this point here is a local optimal solution of this problem 17, but 0,1 is not a local optimal solution of our bilevel optimization problem. So this means we get here some spurious local optimal solutions in this replacement, and this makes it difficult to investigate it, especially also to solve it, because it's the only feasible point. That's 0,1, yeah. The only global optimized solution of the bilevel optimization problem was 0,1,0,1 here. Yeah, and that's another one. Okay, so yeah. Okay, we can also come from a local optimized solution of 15 to a local optimized solution of the, original problem. For this, we need some inner semi-compactness. Inner semi-compactness is satisfied, for instance, if this set KW is uniformly bounded, has uniformly bounded image sets, then we have this semi-compactness. And we can also use local minimizer. Yeah, we have seen that these local minimizers are difficult with respect to relation to bilevel optimization problem. This is given here if this y and z are the same points, and we have a Slater condition, and this is a local minimizer, and that is important for each u. It's a Lagrange multiplier of the lower level problem. Then we come back to a local optimized solution of our bilevel optimization problem. And the point that we have to use all elements in this set KW can we see also here. This point must be a local optimized solution for all of these. And that is not so easy, because to check if it's local optimization for all of these points is rather expensive. What we also see is that MFCQ is violated for the problems that we have seen also in the optimal value transformations, that we don't have MFCQ. Here we also don't have MFCQ. What we can do in solving this problem is, the idea is here we approximate this problem. That is this dual transformation, and we approximate this problem by adding here a positive epsilon 1, and we need to, that's this Lagrangian here, that the Lagrangian is equal to 0. Okay, and that's we approximate a bit that the norm of the Lagrangian is not larger than absolute 2. And then we come also to this. We solve global optimal solutions, or compute global optimal solutions of this problem here for epsilon k tending to 0 from above. And then we have accumulation, consider accumulation points, and these accumulation points are then global optimal solution problems of our problem 15. That is this dual transformation, dual problem transformation, and we know that this is related then to global optimal solution of our bilevel optimization problem. And so this gives us a first idea to solve this problem and to compute a global optimal solution of our bilevel optimization problem. This can also be done for local optimal solutions. We need some more assumption, and this is assumption given here. That is not an easy assumption, but if you compute sequences of local optimal solutions, we know that the local optimal solution is the best one in a certain neighborhood. But we have a sequence of neighborhoods. And if the sequence of neighborhoods shrink down to one point only, then we don't know anything. And the idea here behind this assumption is that this neighborhood does not shrink to 0 or to only 1 point. And that's the idea behind it. If you don't have this, then it works. Okay. Okay, so I have one first replacement, also it was a second replacement, and now I come to the third replacement. Third replacement, that is one which we know all, using the Karl'sch-Kuntagel conditions of the lower level problem. Because this here, these last 4 equations here are the Karl'sch-Kuntagel conditions of the lower level problem. I replace the lower level problem by the Karl'sch-Kuntagel conditions and come to an MPEG. MPEG originally was called MPEG, mathematical program with equilibrium constraints. Later on, mathematical program with complementarity constraints, MPCC. And this, of course, is not a convex optimization problem. And yeah, the difficulty here is that global optimal solutions of the bilevel optimization problem need not to be local optimal solutions of this problem 20. And a global optimal solution of 20 does not need to be feasible for our bilevel optimization problem. This is an old example. The old example comes from Mirlies from 1999. Lower level problem is only minimized to minimize this function here. And the solution of this problem here is given here by this formula. And if we plot this formula, then we come to this function here. Okay, the green is the plot of this function in two dimensions. A global optimal solution of the global optima of the lower level correspond to this part and to that part. That is the solution set mapping of the lower level problem. This red And we see that the global optimum of the bilevel optimization problem is, of course, this point. If we minimize the distance to this point here, then we come to that point. But the local solution of the optima at that point, that's the global one. That is not feasible for the bilevel optimization problem. That is feasible for the bilevel. Okay, that's it's the local optimum of this problem. That works. Okay, but the global, we see, the global solution here of the MPEG is not feasible. Okay, but what can we do? Or what can we say with respect to the relation between bilevel optimization problem and the MPEG transformation? Okay, when we have Slater condition is a lower level problem and global solution of our bilevel problem, and this global optimized solution is a global optimized solution of this transformed problem for all Lagrange multipliers. That is easy. If the lower level problem is convex, constraint qualification is satisfied, and we have a local optimized solution of the bilevel optimization problem, then yeah, it's also related to a local optimized solution of the replacement, but the other way around is not correct. Here we need then this is a local optimized solution for all Lagrange multipliers. That is more or less the same idea which we have also seen in this duality idea. And that's a set of Lagrange multipliers, okay. Yeah, that has also been done for pessimistic bilevel optimization problem. I speak only about the optimistic one. Okay, then we come back to the example. That's the same example again. Yeah, and if we check this, then we come again to this point here, 0, 1, x is 0 and y is 1. And this point is local optimized solution of the MPEG, but not corresponding to a local optimized solution of the bilevel optimization problem, because the bilevel optimization problem has no local optimized solution besides the global one. Okay, and yeah, and if we look at this condition, then here we have to solve our bilevel problem for an infinite number of points, or we have to check an infinite number of points for local optimality. And this cannot be done. So the question is it, can we avoid this difficulty? Okay, this difficulty is related to non-unique Lagrange multipliers. If you have a unique Lagrange multiplier, all is fine. You have a unique Lagrange multiplier if you have LICQ, linear independence constraint qualifications, be satisfied. So is the linear independence constraint qualification generically satisfied? Generically satisfied means that if the problem is not satisfied, then we have only to use a small perturbation of the problem to satisfy it. But that is correct. It is generically satisfied if we have if we have linear, or no, if the lower level constraint does not depend on x, then it's correct. I saw that Rema is attending this webinar. If it's correct, then Rema can say a bit more about this property, because she investigated it in her PhD thesis. Okay. In general, it's not the case. It's not generically satisfied, because we have seen at the beginning in this example, I've given a plot of this example. If you perturb the problems a bit, then nothing changed. Yeah, maybe the global optimum moves a bit, but this difficult local optimized solution of the MPEG moves a bit, but does not lose the properties that it's not related to local optimized solution of the bilevel problem. Okay. Yeah. If you want to solve it, this MPEG transformation, then we use again, or we can use one possibility. We have we have a very large number of approaches for investigating or for solving MPEGs that we know it. Many people did it. But the difficulty of this local optimality condition has to be solved. And for that, we can again approximate our problem. Yeah, that's more or less the same idea. I've shown already some slides again. Here, this perturbation we have seen already, and here's the perturbation of the complementarity slackness conditions. And if we do that, and consider global optimal solutions for epsilon tending to 0, a sequence of global optimal solutions, then it converges, or the accumulation points are global optimal solutions of the bilevel optimization problem. That can be done independent of the norm we use here. And if you use Manhattan norm here, then this means that we have only a number of inequalities, not quadratic. It's only here that is the subgradients of the subderivatives of the Lagrangian with respect to all y need to be bounded by epsilon 1 themselves. And so this is not a difficult problem here. And we can also do it for local optimized solutions. There we need again one condition, and this condition is again related to these neighborhoods here. It's the same, and then we can also use a sequence of local optimized solutions, and this works then also. Okay, then I have some references, small number of references, and then I think my time is more or less over. And I thank you for attending me, for listening,